Hello, my dear friend. Welcome back. My name is David Cortese, and this is my website www.david-cortese.com. In this video, I'm going to talk about an important topic, the programming paradigms. So let's start. Let's read together this document. You can download this document from my website. You can find it in the section Software Engineering. So let's start. Programming paradigms introduction. Programming paradigms are fundamental approaches to writing software, each providing distinct techniques, philosophies, and structures for solving problems. A paradigm influences how programmers think about structuring their code and how they approach problem solving. This document aims to explain the major programming paradigms, their core principles, and their strengths and weaknesses, enabling a deep understanding of how each paradigm works and its appropriate use cases. Imperative programming overview. The imperative paradigm is one of the oldest and most widely used approaches to programming. It focuses on how a program operates by describing a sequence of instructions for the computer to follow. This is akin to giving a detailed step-by-step procedure to achieve a task. Characteristics, state and control flow. In imperative programming, programs have a clear state that changes throughout assignments and statements. Control flow is explicit, with loops and conditionals playing a prominent role. Sequential execution. Instructions are typically executed in the order they appear, though the flow can be altered using control structures like loops and conditionals. Key concepts: variables and assignment. Variables hold data, and assignment operations update these variables. Loops and conditionals. Structures like for, while, and if control the program flow by specifying repetitive and conditional behaviors. Procedures, functions. The program's actions can be abstracted into procedures or functions, making the code modular. Strengths: easy to understand, especially for small programs. Maps closely to the hardware's operation, making it efficient in terms of performance. Well suited for low-level systems and procedural languages like C. Weaknesses: managing complex state and control flow can become difficult, leading to bugs. Not inherently modular or reusable, though these can be imposed through structure. Examples: languages: C, Python supports multiple paradigms. Assembly language. Procedural programming overview. A subset of imperative programming. Procedural programming breaks down a program into procedures, and also known as functions or routines. It emphasizes code reusability and modularity by allowing common sequences of instructions to be encapsulated and reused. Characteristics: procedures. Central to this paradigm, procedures encapsulate tasks that can be invoked throughout the program. Top-down approach. Programs are typically designed using a top-down approach, breaking larger tasks into smaller sub-procedures. Key concepts: procedure calls. Tasks are executed by invoking a procedure. Local and global variables. Procedures can have their own local scope, promoting encapsulation and reducing side effects. Strengths: encourages modular code design, making it easier to maintain and understand. Code reusability through procedures helps in reducing duplication. Weaknesses: like imperative programming, managing large states and complex interactions, can become challenging. Procedural programming often lacks the abstraction mechanisms available in more advanced paradigms like object-oriented programming. Examples: languages C, Pascal, Basic, Python in procedural style. Object-oriented programming OOP. Overview: object-oriented programming centers around the concept of objects, which combine both data, attributes, and behavior methods into a single entity. OOP focuses on modeling real-world systems through classes and objects, promoting code reuse, abstraction, and encapsulation. Characteristics: encapsulation: objects encapsulate their internal state and expose behavior through methods, hiding implementation details. Inheritance: a class can inherit attributes and behaviors from another class, promoting reuse and extending functionality. Polymorphism: different cases can be treated as instances of the same class through inheritance, allowing for flexible and scalable code. Key concepts: classes and objects. A class defines the blueprint for objects. Objects are instances of classes that interact with one another. Abstraction: by hiding complex implementation details and only exposing necessary functionalities, OOP promotes simplified interactions. Encapsulation and information hiding: objects' internal state can be hidden from the outside, preventing unauthorized access and modifications. Inheritance and composition allows for building hierarchies and reusing code across similar objects. Polymorphism: the ability for different objects to respond to the same method call in different ways, like method overloading and overriding. Strengths: promotes reusability through inheritance and composition, enhances modularity by encapsulating data and behavior, easy to extend and maintain due to its modular structure, excellent for modeling real-world entities. Weaknesses: overhead in both performance and complexity can arise due to abstraction. OOP requires careful design upfront, which may slow down initial development, not suited for all types of problems, particularly where simple, procedural solutions are more effective. Examples: language Java, C++, Python supports OOP and Ruby. Functional programming overview. Functional programming is based on mathematical functions and avoids changing state and mutable data. This paradigm emphasizes what to compute rather than how to compute it, contrasting the imperative approach. It treats computation as the evaluation of mathematical functions and avoids state changes. Characteristics: immutability. Variables in functional programming are immutable, meaning once a value is set, it cannot be changed. First-class functions. Functions are treated as first-class citizens, meaning they can be passed as arguments to other functions, returned as results, or assigned to variables. Pure functions. Functions always return the same result, given the same input with no side effects. Key concepts: recursion. Functional programs often rely on recursion instead of loops for repetitive tasks. Higher order functions. Functions that take other functions as arguments or return them. Closures. Functions can remember the environment in which they were created. Lazy evaluation. Evaluation of expressions is deferred until their results are needed, optimizing performance. Strengths: modularity. Pure functions are highly modular and reusable. Testability and debugging. Since functions have no side effects, they are easier to test and reason about. Concurrency. Immutability and statelessness make functional programs ideal for parallel and concurrent execution. Weaknesses can be less intuitive for developers, accustomed to imperative paradigms. Recursion and immutability can lead to performance inefficiencies if not handled carefully. Examples: languages: Haskell, Lisp, Scala, F#, Erlang. Logic programming. Overview. Logic programming is based on formal logic and focuses on what the problem is, not how to solve it. In logic programming, programs are written as a set of logical statements that describe facts and rules about a problem domain. The logic engine that infers the solution by querying these facts and rules. Characteristics: declarative. Instead of defining the sequence of steps to solve a problem, logic programs declare facts and rules. Inference: solutions are found by applying logical inference on the rules and facts provided. Key concepts: facts, basic assertions about objects or relationship. Rules, conditional statements that define new facts based on existing ones. Queries, questions asked of the logic engine, which it tries to answer based on the facts and the rules. Strengths: very expressive for solving problems involving constraints and relations. Naturally suited for tasks that involve complex logical inference or pattern matching. Weaknesses: may not be efficient for performance-critical applications. Limited support for handling immutable states or side effects, which are essential for many types of programs. Examples: languages, Prolog, Datalog. Declarative programming. Overview. Declarative programming focuses on what the program should accomplish rather than describing how it should achieve it. This paradigm abstracts away the control flow and steps of computation, leaving the execution engine to figure out the how. Characteristics: descriptive. The programmer describes the desired results, and the underlying system determines how to achieve them. No explicit control flow. Unlike imperative programming, control structures are abstracted away. Key concepts: statements of fact or logic. Code typically consists of high-level declarations of what the end result should be. Queries: programs often consist of querying or specifying properties that must be satisfied. Strengths: simplifies programming by removing the need to manage low-level details, reduces side effects and state management. Weaknesses: limited flexibility in some cases, since the control over how tasks are performed is relinquished. Performance can sometimes be less predictable due to the abstraction of execution details. Examples: languages, SQL for database queries, HTML for web structure, Prolog. Event-driven programming. Overview. Event-driven programming revolves around the idea of events triggering specific responses or actions in a system. Programs designed with this paradigm typically involve systems that react to external or internal events such as user input, sensor data, or network messages. Characteristics: event handlers. Specific functions or methods respond to events such as mouse clicks, key presses, or network requests. Asynchronous behavior. Programs may need to wait for external events and respond asynchronously when they occur. Key concepts: event loop, continuously listens for events and triggers appropriate event handlers. Callbacks, functions that are executed in response to an event. Asynchronous programming, handling events without blocking the main execution thread. Strengths: highly suited for interactive applications such as graphical user interfaces, GUIs, games, and networked systems. encourages the development of modular responsive systems. Weaknesses can lead to complex code structures, especially when managing multiple events or asynchronous behavior, difficult to debug and maintain in large systems due to nonlinear flow. Examples: languages JavaScript, particularly for web development, C# with event handling for GUIs, Python with frameworks like Tinker. Conclusion: each programming paradigm offers unique advantages depending on the problem domain, performance constraints, and the programmer's expertise. By understanding the principles behind these paradigms, developers can select the most appropriate approach or even combine paradigms when building modern software systems, ensuring the most efficient, scalable, and maintainable solutions for complex tasks. So you can find this document on my website www.david-cortese.com, exactly in the section software engineering. On my website you can find a lot of information about software engineering, web development, mathematics, physics, chemistry, but also games like chess, apps, music, other documents, and so on. You can chat with me using my personal chat. You must sign up using your email. And dear friend, your donation is important. Help me update this website and join this community. Thank you for watching. See you next time. Bye bye.